Good afternoon to you, my dear students out there and everyone out there. Teacher Kakuri is in the house, and I want to welcome you today to our afternoon lesson. Before we start our lesson, allow me mention one, that the teachers running the teaching program on BBS TV and the management have come up with an app. It's called School Kit. School Kit can be downloaded on your phones, on your computers. Go to Play Store and look for, just type in School Kit. You'll be able to see the first item there. There are several items, but the first item. Install it on your phone. We are going to be using that application to reach students even after we have left the studio. We shall be putting a lot of work to answer very many questions that you've been asking us away from the lesson. I want also to remind you to continue getting access to the work on my YouTube channel and continue revising. Before I start the lesson, I want to share with you a few tips that can motivate you. One that I have experienced over time is that we have students who normally categorize under the geniuses and those that work hard. And I have noticed over time that a student that is hardworking can actually beat a student that is naturally gifted. Those are the ones we call geniuses. Naturally gifted, but not hardworking. So hard work can beat a natural gifted student if they don't work hard. Number two is that if success was a building, then if you want to achieve it, you cannot simply achieve it by taking a lift. You can't simply achieve it by taking a lift. You must take the steps or the stairs. Students, you are not going to sit there and expect to get a distinction, expect to get a principal A when you are not doing the hard work. Last for today is that if there is anyone that has never made a mistake in life, this can even be general. If there is anyone that has never made any mistake in life, then they have never tried to do anything new. They have never tried to do anything new. Today we shall be starting a new topic. I come now to the lesson. We shall be starting a new topic, and the topic is right on the BB, friction. Of course, this is applied maths, and I want us to start the introduction of this topic together so that we can move consistently together. In mathematics, we don't do a lot of rugambo, but allow me to define what friction is. Whatever we'll discuss over here is very important. However, students should note that in mathematics, they are not going to ask you to define friction, but you need to understand what friction is if you are going to be able to attempt or to interpret questions correctly under this topic. Friction is also a topic or a concept we look at in physics, and we define friction as a force that opposes the motion of two bodies that are in contact. A force that opposes the motion of two bodies that are in contact. I could even say, paraphrased, that friction is the force that opposes relative motion of two bodies in contact. Relative motion. Therefore, I will quickly mention in a layman's language that if you are going to buy shoes, usually you check whether the sole is still okay. If the sole is worn out, on a rainy day, you can be sure you have very high chances of falling down because the shoes are not gripping very well with the ground. Similarly, those who use automobiles, all of us use motorcycles, cars, and whatever. The tires must be good enough on a very rainy day for the drivers, the riders, and as I've said, the pedestrians, the shoes, the soles of their shoes. They should have a very good contact with the ground if they must walk consistently. So we are looking at a topic that is going to allow us understand how friction affects motion. How friction affects motion. And I will say, like I've said, the friction, this is the force that opposes motion of two bodies in contact, in brief. And one common word that you'll meet under this topic is the word rough. When they say that a body is placed on a rough surface, that word rough, wherever you meet it, will imply under this concept that there is a friction acting. It will imply that there is friction acting. It will imply that there is friction acting. We shall consider, before we look at the first consideration, the other thing that we need to note is that since friction opposes motion of bodies that are in contact, it means it acts in the opposite direction. I should also put this one here. It acts in the direction, that is opposite to the direction of motion of the body. These two facts are very important. And I have mentioned that when they use the word rough, let us know that there is friction. Let us consider. We are going to consider a body of mass m. We are going to consider a body of mass m kilograms. The body has a mass m kilograms and is moving on a rough, I will underline this, on a rough surface, a rough horizontal to start with, horizontal surface. The forces that act on this body, can be shown in the diagram. Overleaf. I am going to put the diagram on our next page. If I consider that as the rough horizontal surface, and I consider this as the body whose mass is m kilograms, therefore this body will have the first force will be the weight, which I'll call W. But from our earlier lesson, sometime when we had just started this program, we know, and from the knowledge of physics, we know that weight is given by mass times acceleration due to gravity. The other force that will act on this body is going to be the normal reaction. We shall use letter R, but we shall be giving a key to define these different symbols. We have said that this body is moving on a rough horizontal surface. If I let the body move in this direction, then we are going to have another force. I will use symbol P that we shall define as the pulling force or the applied force. And then we shall have the frictional force indicated over here. I will call it F. And we shall say where P is the applied force. That implies that the direction of motion is this. I can put this to indicate direction of motion. The body is moving, according to me, from right to left. According to you, it may even change the direction because what you are seeing may be a reflection of what I'm writing, an opposite reflection. So P is the applied force. F is going to be the frictional force, which we are soon to know. And R is the normal reaction. R is the normal reaction. What else? W is the weight of the body. It is important that at this moment I say that F is going to be given by mu R, where mu is defined as the coefficient of friction. These are the forces acting on that body, and I have ably defined what each symbol there stands for. In some books, you will discover that R is sometimes substituted by capital N. Those two symbols or letters are interchangeably used to mean the normal reaction. Normal means at 90 degrees. Normal means at 90 degrees. The friction force must be indicated at the point of contact of the two bodies we are talking about in this case. The body must be in contact with a rough surface for frictional force to happen. And we are saying that frictional force is given or is equivalent to mu, where mu is a constant, is a letter that represents the constant of friction that we call the coefficient of friction. That we call the coefficient of friction. I will be clearing the first page where we had our definitions shortly so that we can proceed. Introduction of a topic is something that must be taken slowly but steadily, such that all the students that are following up this program are actually able to understand. And I always tell my students that if you want to understand, you must be able to be a good listener, and you must also be interested not only in the content, but in the person that is giving you the content. You must love the teacher. You must fall in love with the subject that the teacher is teaching. That you feel like you don't want to miss a lesson. We proceed from here. I want to say that I am very sure that most of the S6 students in various schools, most of the S6 students in various schools had not captured or covered this topic, especially in applied maths. They could, those who do physics could have covered friction already. That one I'm very sure. But those who do mathematics, very few, if any, could have covered this or had covered this by the time of close down. Now, we have already introduced the forces acting, and we want to talk about limiting equilibrium. When do we say that there is limiting equilibrium? When do we say that there is limiting equilibrium? If I would have demonstrated, but I am just going to describe. If I have a calculator, and I put, unfortunately I don't have a book here, so I'm not going to demonstrate. But if I put a calculator on top of an A4 book, and then I slowly begin tilting that calculator, when I begin tilting the book, which is carrying a calculator, the calculator will not start moving immediately. But a point will reach where that calculator will start moving or attempt to start moving. Now, the force that is responsible, the actual force that is responsible at that particular point where the body just begins to move, is what we are going to look at as the limiting, or the force at limiting equilibrium. It's what we are going to look at as the force at limiting equilibrium. So I was trying to explain what we call limiting equilibrium. Limiting comes from the word limit, and equilibrium is basically a state of balance of a body. I'm not going to define the terms beyond saying them, because as I told you, that would now be entering into physics. But you need to know that when they say the body is in equilibrium, it means that the forces acting on that body on either side are actually equal. The body is in balance. The body cannot move. I talked about that in our very first lesson when the lockdown started. Now, limiting, we are saying it comes from the word limit. So we can say that limiting equilibrium, I will use this to represent limiting equilibrium. This indicates, limiting equilibrium indicates that the body is at rest. It indicates that the body is at rest, but on the point of beginning, it is at rest, but on the point of moving, Limiting equilibrium is a statement that we use to indicate that the body is at rest, but it is on a point where it wants to start moving. And we can therefore say that the maximum force, we shall call it F max, F subscript max, the maximum force that causes motion of this body to occur, is what we are calling limiting friction, is therefore going to be given by an expression that we shall say F max will actually be equal to mu times R. F max will be given by that expression, mu times R. I already told you, but I can still say where R and mu carry their usual meanings. Their usual meanings here is, I am using it because I already defined these terms, which fortunately are still available for all of us. So the maximum force that is responsible to cause motion of a body that has been at rest is what we are calling mu times the normal reaction. Is what we are calling mu times the normal reaction. Candidates should note that sketch diagrams of illustrating the theory about the statement of the question must be drawn, and all the forces acting on these sketch diagrams should be shown properly. We move to another important concept. Remember that teaching is best done when we begin from what we know and move towards what we don't know. If I had a physical class right over here, I would have started by asking you what is friction like I defined it. I would have started by that. Now we are going to look at the angle of friction. Angle of friction. Again, the angle of friction must be defined. And I will define this briefly, but this is for purposes of equipping my learners. I want to repeat that in mathematics, unless it is done on a normal school setting, but in the national exams, you're not going to find a question in mathematics asking you to define friction. That one you're not going to find. But you must be having the theoretical interpretation of what friction is. Now, the angle of friction is basically the angle that is made between the normal and the resultant line of force, or the resultant line. It does not necessarily mean it will always be force, but here we shall majorly be dealing with force. So we can say that this is the angle between the normal, the angle made between the normal and the resultant line of force. Let me use force and the resultant line of force. If I illustrate and I let this be my normal, remember, okay, I can attach a body here for purposes of emphasis, because some people will say, where did the normal come from? We said the normal is R. If my resultant line is this one, and the distinction between any other force and the resultant force is normally those two arrows, then I am saying that the angle that is made here, we usually use the symbol of lambda. In physics, we call that symbol wavelength, but here we call it lambda. That angle would be looked at as the angle of friction. Now, I want to derive a few things here, because I told you that there must be a friction force here. There must be a friction force here, and this force, I think you are beginning to note that we can substitute it with mu r. You are beginning to note that we can substitute it with mu r. I am going to let my resultant be denoted as P. I'll let P be my resultant, and I must put it in writing. Let P be the resultant force. Again, we will borrow from the concept that we already covered partly on resolving of forces. We shall find the concept of resolving of forces, which we did some time back. Very, very, very important as we cover this area. Now, from this diagram, we are going to look at several other issues. If I complete this to give me a parallelogram of forces by extrapolating this and dropping this, I can tell you that this force F is the same as the force there, and this is also R. Even here we have F. As long as we maintain the direction that F is going this side, even the F, because this is a rectangle, we call it a parallelogram, the two opposite sides are is equal, and therefore if I take the turn using trigonometry, I am going to take the tan of lambda. My tan of lambda, trig states that tan is opposite, lambda is here, so this becomes the opposite side, and this becomes the adjacent side. So my tan of lambda will become the opposite, which is F, over the adjacent, which is the normal reaction. But note, I will put a but, that all of us know that our F is equal to mu R. Our F is mu R. Therefore, it implies that my tan of lambda, if I substitute for F, is now going to be equal to mu R, which is my F over R, implying that my tan of lambda is actually equal to mu, which is the coefficient of friction. My tan of lambda is actually equal to mu, which is the coefficient of friction. If the intention is to find the angle of friction, we can proceed and therefore say, hence, our lambda can be got as the arctan of mu. Our lambda can be got, or our angle of friction can be got as the arctan of mu. Arctan is written like that. I hope we are still together, my dear students. And whenever you see that the blackboard is full and you have not captured everything, kindly remember to use technology by taking a shot, and then we progress. Remember, I told you that if you sometimes, because it is inevitable, if you sometimes enter in a lesson, especially in a lesson very late, and you are lucky they allow you in, then you must not struggle to catch up with the teacher starting from the very start of the lesson. Just identify how much space has been captured before your presence. Estimate by comparing the handwriting of the person you are checking with your own handwriting, that is inherently. And then after estimating, start right where they are. If you are fast enough in between, you can be chipping up by capturing the work you missed once in a while if you are fast enough, such that by the end of the lesson you are actually at par with the rest of the students. If you are not fast enough, please be consistent with the teacher and put in time to capture whatever you missed outside that lesson. I will definitely be clearing off this first part, but we are still continuing with the interpretation of that diagram. And after interpreting that, I think we shall be good to go with examples, at least the first example. Like I said, I will chip in and tell you that whatever you do not understand here, if you install that school kit app, we shall be putting most of this work there, and you'll be able to contact us even after our airtime on air or after our lessons. Now we proceed from there. We want to find out the value of P. We want to find out the value of P there, and we shall proceed by saying, to find the expression, which ideally is the same as the value, the expression for the resultant force. To find the expression for the resultant force, which on our diagram is P, you will notice that we now have, let me draw it here. If I pick just one of the triangles, we have two congruent triangles. If this is our resultant, which is P, this force here is F, the frictional force, which is mu r, and then this force is the normal reaction. This is a right-angled triangle. Whenever we are looking for the resultant, the correct vector diagram must always have the resultant starting from the point where the two forces are acting. The two forces are R and F. So the resultant must connect there. And vectorially, if I were to put A, B, and C, you can see that my resultant, which is AB, which is P in this diagram, should be equivalent. If you are at A and you want to go to B, you can pass AC and pass CB. That is according to vectors. So to find P, we shall use Pythagoras theorem. Even now, probably a very good primary student, if they do it without using that, should be able to get the answer. Pythagoras theorem will give us that P squared, being the hypotenuse, will be equal to R squared plus F squared. But I am going to substitute for F here. If I use that, I must tell the examiner that, but I know F as mu R. So my P squared will be equal to R squared plus mu R all squared. Now, my mu R squared will give me R squared as a common value. I will factor it out, and I will stay with 1 plus mu squared. And therefore, I will say that my P is actually, if I am interested in finding P, my P will be equal to this, the square root. It will be equal to R into the square root of 1 plus mu squared. I want to express it differently. Again, I will say that since we know that mu is equal to tan of lambda already, we can say that it implies that mu squared is equal to tan squared lambda. In trigonometry, we know, I am not going to emphasize this, I'll simply quote it. We'll say, but sec squared lambda will actually be equal to 1 plus tan squared lambda, which will imply that actually sec squared lambda or tan squared lambda, okay, sec squared lambda will be equal to 1 plus mu squared. Since our mu squared is tan squared lambda, we substitute it here. And therefore, it implies that what I have here in this bracket, I can substitute it with sec squared. This would imply that my P would actually be equal to R into the square root of sec squared lambda, since 1 plus mu squared is sec squared lambda, implying finally that P is equal to R sec of lambda. P becomes R times the sec of lambda. Now, most of these details must be brought out because a very good teacher can actually challenge students that if a force, if a resultant force P acts on a body of known mass, say m kilograms, that is in contact with a rough surface, show that the resultant force P is given by R sec lambda, where R is the normal reaction and lambda is the angle of friction. This is a very good question that can be brought, and we ask you to show that the resultant force is given by R sec of lambda. Students should note here that the symbols P is not constant. You can use any letter as long as you define it. But I will be quick to caution that it is important to stick to the letters usually your teachers use, because if you assume your own letter from experience, you assume to change your own letter by the end of the number you have brought in the letter the teacher used in class. And even if the working is okay, now the symbols will be different and you definitely cannot score. You definitely cannot score. I will give some airtime for you guys to capture this. And after this, we are going for examples. After this, we are going for examples. That means I will be clearing off the other side and probably write down the example as you capture the page I did last. Yes, our question is ready. Our question is ready. And we shall work through it. The question is ready. We shall work through it very fast. It is very brief. I will subdivide my workspace there to do part A over here, and the part B will be done over there. It does not take a lot of time. I told you that the word rough automatically means there is friction. They want us to calculate the maximum frictional force which can act on a body of mass. I told you it is important to sketch. If we sketch this body whose mass is 12 kilograms will exert a weight of 12g. The value of g here, in this paper is 9.8 meters per second. The value of g is 9.8. So the weight is 12. The normal reaction, which is R, is there. And they want us to find the maximum frictional force. If we let the body move this side, this is direction of motion, then the frictional force must act this side. And since we already looked at the expression for maximum friction without wasting time, we will note that for equilibrium, this is the abbreviation of equilibrium, the normal reaction R will be equal to the weight, which is 12g. The normal reaction will be 12g, and the frictional force F is equal to mu times the normal reaction. So you only need mu and the normal reaction. So the maximum frictional force which they want is going to be a quarter, which is 0.25. I prefer using fractions if I don't want to use a calculator, times R, which is 12, times 9.8. And when you compute this, you'll get the final force required, as once you compute, it is 3 times 9.8. And 3 times 9 is 27. And of course, 0.8 times 3 is 2.4. And therefore, you must get 29.4. 29.4. I will not stop those who are interested in looking for your calculators to look for it. But in principle, it is important for students to learn to use their heads. I want to emphasize that most of our students have been spoiled by calculators, to the extent that even 1 times 1, some of them, you find them looking for calculators. Since the working is the same, for part B, I am not going to sketch. I have my mu, which is 1 out of the root of 5. The mass is still the same. The R is still the same. So our maximum force here, I would actually ask you to do it. Our maximum force is going to be equal to mu, which is 1 out of the root of 5 times 12 times 9.8. And when you compute this, you should be able to get the maximum force. You should be able to get the maximum force. The maximum force value you should get when you compute that should be approximately 52.59. I want to mention that about the number of decimal places, the minimum number of decimal places should always be 2. You are free to write as many decimal places as you want, but if you must write a minimum number in applied maths, it should be 2 decimal places, unless otherwise stated like we are seeing in statistics, where they tell us to give our answer set to 4 decimal places, 3 decimal places. Otherwise, if it is open, 2 is the minimum. That is our first example. A very nice question. We can move to look at our second example. I usually tell people it is important to bite what you can chew, and it is also important to swallow when the food is well broken down. The biologists will tell you. So I don't want to rush you to do so many things. I want us to take it steadily and be able to understand what we are doing. Our second example. The question says a box of mass 125 kilograms lies on a raft. I want to emphasize this. That word will always be there as long as it is friction. If there is no friction, it will be substituted by the word we call smooth, the opposite. So they want us to calculate the magnitude of the force P. We are in the dying time of our lesson, and I am not going to rush you, so whatever will not be able to finish, we shall pick it up. But if you have to sketch this number quickly, this is our normal reaction, this is our weight. It is mass times G, so it implies that it is now a force. And if we let it move this side, they want us to find the value of P. But they have told us there is friction. And our coefficient of friction is 32 out of 100 times R. In equilibrium, we already saw that in equilibrium, remember we talked about limiting equilibrium. In equilibrium, the upward forces, which is normally represented like that, or with the word, imply that R is equal to 125 G, which we shall say is 125 times 9.8. And this is computed in newtons. And horizontal forces, horizontally, upward is the same as vertically. Horizontally is that. You can use either of these two symbols, or use the word, or use the symbol. The value of P is supposed to be equal to the force F, which is mu R. And therefore, the P that we are looking for is supposed to be 32 out of 100 times the R, which we already have, 125 times 9.8. And when we compute this with our calculators, definitely we should be able to get an answer here. When you compute that with your calculator, you should be able to get an answer. The value that you get there should be 392. 392. And never forget to attach the unit. In mathematics, we say that a unit is like salt in food for someone that is not diabetic. I will interpret the last part and allow you to finish it yourselves. In 3 minutes or so, we shall be done with the interpretation of the last part. Trust that we shall be done. The concept is the same, but slightly different here. We still have our weight, our mass. Our weight is 125 G. This time, they are telling us that P is acting at 45 degrees. So P is acting around here. If I let this be 45, our P is acting here. Our normal reaction is still there. Our R and our frictional force is still there. The technique here is we need to resolve that resolving vertically in equilibrium. Resolving vertically, we have R, this R here, will be joined by the component of P here, which is P, the sine of 45. When we resolve this P here along this line, it has a component, and it also has a component along the horizontal. So in equilibrium, forces going up, R plus this, should be equal to 125 G. R plus that should be equal to 125 G. And we can therefore keep it as A. Resolving horizontally, we shall have that P times the cos of 45 degrees when we resolve along here in equilibrium will be equal but opposite to mu, which is 32 out of 100 times the mg, 125 g. Will be equivalent to that. Therefore, you are supposed to solve these two numbers by substituting. If we choose to say this remains mu r, it is faster. From A, our r is 125g minus p, the sine of 45. So if we substitute in B, our P cos 45 will be equal to 32 over 100 into R, which is now 125g minus P sine 45. I will ask you to complete this. Complete this and find the value of P. Open brackets, rearrange. If you open brackets and rearrange, mu times P will come this side, and you will be able to get P. I could quickly say that your P into the cos of 45 plus, it will be plus 32 out of 100 times P times the sine of 45, because the P is out, will be equal to 0.32 times 125 times 9.8. So our P will be dividing these two expressions. You divide and get the answer. I will challenge you to look up for numbers for now. When we meet for our next lesson, that's when I will give you more numbers under this area. I remain teacher Kakuru Dennis. I want to thank those that have been attending this lesson and wish you the best. Remember, hard work breaks no bone. God bless you. Gachali Mabaga.
Ssomera Muddiiro lyo ng'ewagiddwa Maryland High School erisangibwa Entebbe. Ssomero ly'abawala n'abalenzi tusomesa arts ne sciences okuviira ddala ku senior esooka.